As a prelude to considering our first directory-based protocol, let's take a look at the main memory states and network transactions that it uses. Now, in the cache, the protocol behaves exactly like MESI. Transitions between the states occur on the same events. But in main memory, it's quite different. It also has to have directory states in main memory, not just in cache. Of course, there are directory entries in main memory, and each one of the directory entries for a block keeps track of whether it's in one of three states. It's either in state EM, S, or U. EM stands for exclusive or modified, and we don't need to make a distinction between the two because main memory doesn't know when a cache that has read a block then writes the block, causing it to transition in the cache into state M. All main memory cares about is that it's in one place and only one place in the cache. If it's in more than one place in the cache, then it's shared. And if it's not in any place in the cache, then it's called unowned. Now, the network transactions for coherence have some similarities with the transactions that we saw in bus-based protocols. And indeed, those transactions that work the same way I've shown in green on the slide. One of the main differences is that in a directory-based protocol, a request is sent to the home node, and then the home node needs to reply. So we have two reply transactions. One where it's a read request, and then it responds with the data to the requester. On the other hand, if it's a write request, we're going to need to find out the sharers. That is, the node that wants to write the block is going to need to find out the sharers. So it asks the home node what the sharers are. And then we get a reply ID transaction. The two write-back transactions are not that different from what they are in a bus-based protocol, but here we explicitly ask for a write-back and invalidate or a write-back and intervention. In the case of a write-back and invalidate, there's a block that is potentially in modified state in some cache, and we need to write the block, so we need to have that copy invalidated, and the data, if it's been modified, needs to be written back to main memory. In the case of write-back and intervention, this is a situation where a block is present in EM state as far as the directory knows, and somebody wants to read the block. Now it's going to have to change state in the cache to state S, and so it's also going to change state in memory to state S. That's what the write-back and intervention does. Then there are two transactions acknowledging an invalidation. And the invalidation needs to be acknowledged so that the owning cache knows that there are no more copies present in the other caches, and it can go ahead and write it. So first we have an invac, where the sharer or owner, that is, any cache that had a copy of the block before, acknowledges an invalidation message and says, I've gotten rid of the block. Then we have a flush plus invac, where we need also to flush the block to main memory. That's the case where it was in modified state in one cache. And then we need to acknowledge the invalidation plus write a copy back to main memory. So having set the stage, we're now ready to go ahead and take a look at the animation of the full bit vector directory-based protocol.